So in order to solve this problem, you have to have a diagram. And in this case, I drew out the diagram for you. On the test, however, you'll have to draw it by hand. Okay, in order to solve this problem, we understand that this is an equilateral triangle, and each interior angle is trisected by a pair of rays. The rays are right here. And trisected means divided by 3. So each angle is divided by 3. So each angle is 20 degrees. So you can label it as so. 20 degrees, 20 degrees. And it also says it's asking for the degree measure of this hexagon. And the hexagon is the intersection of the interiors of the middle 20-degree angle at each vertex. So the interiors of the middle 20-degree angle, this is the middle 20-degree angle at each vertex, and the intersection of the interiors, so everything in it, right here, is this center part right here, this hexagon looking shape right here, and it's asking for the smallest angle of this hexagon. So we will have to do some angle chasing. Okay, so since this is 20 degrees and all the sides are congruent, that means these two bases, these two angles are 80 degrees each, because the sum of the angles of a triangle are 180. So these two are congruent angles at 80 degrees each. And we can go further by finding that 20 degrees right here. Wait, hold on. 20 degrees right here. This is because it's a straight line. The supplement of 80 degrees is 100. So that means this angle right here is going to be 60. Now we have vertical angles. So this is 60. In order to perform angle chasing, you must know a lot of different geometry theorems and everything like that to understand more of the figure that you're working with. So since this is 60, we have this is also 120 right here, 120, and then because they are similar, 120 right there. And then since this is a 5-sided shape, that means the interior angles will add up to 540, and we already have 200 times 2. That's 400. So that means this angle is 140. And now we're closer to the middle, as you'll see right here. So this angle, because of vertical angles, 140 as well, and 140 as well. This is 40. That means this is 100. No, this is this is 40, and this is 60. That makes this 80. So that means this angle, which is another angle part of the hexagon, it's 100. There's probably faster ways of doing this angle chasing. So yeah, there's 100 right there, 140 right here. And if you do all the angle chasing, you'll find that 3 of the angles are 140, 3 of the angles are 100, resulting we can double check our answer. 420, 720 is the total interior, the sum of the interior angles of this hexagon, which is correct. So we're trying to find the smallest angle of this hexagon, and that is 100 right here. Now we're going to move on, and there are 2 main ways that you can solve it. Number 1, you can either use long division or synthetic division. any form of division with polynomials that will work, or you can use the Chinese remainder theorem. And within we'll talk about both methods. The second one is more for experienced people that know the Chinese remainder theorem. Okay, so let's start with method one. Method one, we have the polynomial x cubed plus x squared plus x plus b. And when you divide by x minus 1 using the synthetic division, it should be easy to get a remainder. Easy to find the remainder, and you will most likely get the remainder of a plus b plus 2. And you can do that for both division instances. And when you divide by x minus 2, for example, you should get a remainder of 2a plus b plus 12. And again, I won't do on here because it will take a lot of time. It'll be very messy. And if you know how to do synthetic division or long division, it should be pretty simple to get it. And this helps us solve because, again, the problem gave you that the remainder for the first one is 4 and the remainder for the second one is 6. So we're essentially just solving a system of equations. So a plus b plus 2 is equal to 4. And then 2a plus b plus 12 is equal to 6. And then you solve a plus b is equal to 2 from the top equation. 2a plus b is equal to negative 6. Nothing too complicated here, just knowing what you have to do. So we solve this system of equations. We find that b is equal to, we multiply by 2. Let's see, b is equal to b is equal to 10. And then a is equal to negative 8. And then we can just find out that b minus a is just 10 minus negative 8, which is just 18. So we have the answer E. And using the Chinese remainder theorem in the second instance of solving it, second method of solving it, we can verify our answer. So in the Chinese remainder theorem, we can essentially just plug in the value of 1 into the equation. So we have 1 cubed plus 1 squared plus a plus b, and we get a remainder of 4. And then we plug in 2 from this, from x minus 2 into the equation again, and then we equate it to 6. So 2 cubed plus 2 squared plus 2a plus b is equal to 6. And we see that we have the same answer as before. We just solve another system of equations with the same, that is exactly the same. 8 plus 4, 12 minus 12 is equal to negative 6. And then we see that b is once again 10, a is negative 8. And then we have the same answer, which is E. So we have 2 instances on how to solve it, and we get the answer E. Now we're going to move on to problem 8. So let's start with 0. 0 statements are false. 4 statements are true. So we obviously know that all these statements can't be true for a couple of reasons. Number one, if at least 2 of these statements are false and that statement is true, that means there has to be at least 2 that are false. And obviously this does not work. And now let's go to our second scenario. We know that this first case does not work. So we're going to cross it out. Now we have 1 false and 3 true. 1 false and 3 true. And we can do casework based on this. Let's say this one is false and the rest are true. this again wouldn't work because at least two of these statements are false. At least two of these statements are false. So that means there has to be of two of the four that are false, and that wouldn't work because only in this case there's only one that are false. So the only possible instance where this would work is if the statement that said at least two of these statements are false is actually false itself, and everything else is true. And let's double check. At least one of these statements is true. That's correct because there are three truths. At least two of these statements are true. Yes, that's correct. There's three truths. At least two of these statements are false, and there's only one false, so the statement has to be false. At least one of these statements is false. That's true. So we realize that this instance works. Three truths and one false. And then we just pick based on how many false statements did Agnes write on his paper. That's one. So the answer is B. So in this case, we can just use casework, but we used very smart casework by starting off by using common sense and logic for this problem. Now we're going to move on to problem 9. So we can kind of visualize this on a graph. We have point 125 here. And essentially what we're trying to do is make sure that this graph passes through, once a value is inputted to x minus a, that it passes through 125. Or how many times it does pass through 125. And we can use multiple different methods here, but one of the prominent ones is just substituting 125 into the equation. So we have 25 is equal to 100 times 1 minus a, because 1 is equal to x in this point, because it has to equal 25. Okay. Anyways, 300 times 1 minus a squared plus 200 times, and then we have 200 times 1 minus a, and we can simplify this by dividing by 100. So we have 1/4 is equal to 1 minus a cubed minus 3 times 1 minus a squared plus 2 times 1 minus a. And to make our lives much simpler, we can substitute y for 1 minus a. So we have y cubed minus 3y squared plus 2y is minus 1/4, because we brought the 1/4 over. And you can use the rational root theorem, I believe, to test if there's any roots that satisfy, or rational roots that satisfy it, or most likely in this case will be irrational and imaginary numbers that work for the solution. But we're not going to test it here. There, you can simplify this, and I believe you do get. You can factor it. You can factor it and simplify it, and I believe after you do that, you do get. You do get three real solutions, three real numbers that satisfy the point on this graph. So the answer for this problem is C. And if you do want me to go more in depth on this, I will, and I'll explain it in probably a later video. Now we're going to move on to our final problem, problem 10. Okay, so to solve this geometry problem, in fact, we need a little bit of algebra. And we can set the radius of the larger semicircle as R, capital R. We can set the smaller semicircle, the radius of the smaller semicircle, as lowercase r. And as you see here, we can write two different equations from this. So since this is from the center, this radii is from the center and perpendicular to the chord CD and parallel, not parallel, but AB is parallel to CD, we have a right triangle that we can form. So this is exactly half of CD. So now we have because this from the center to C is one radii, a large radii of the larger semicircle, which is capital R. We find that an equation is 64 plus r squared is equal to capital R squared. Because again, right triangle right here. Another equation that can help us find the area of the resulting figure that is shaded is by finding the area of this larger semicircle, subtracting it by the smaller semicircle. So the area of the larger semicircle is pi capital R squared divided by 2. The smaller one is pi r squared divided by 2, lowercase r squared divided by 2. And then we can just substitute it in, and it should cancel cleanly. So we substitute capital R squared into the equation. So we have r squared plus 64 times pi divided by 2 minus pi r squared divided by 2. And then we just do pi r squared plus 64 pi minus pi r squared divided by 2. And we get 64 pi divided by 2 equals 32 pi. So that gives us our answer of 32 pi, which is C.